Hi everyone, I'm Oskar. I'm going to talk about the work that I did during my Maths Fellowship program. You heard about that program from Ryan yesterday. I'm very grateful to them for setting me up with my wonderful collaborators, in particular my primary co-author, Kurt Tiggs, and our two mentors during the program, Atticus Geiger and Neil Nanda. The work that we did was in the field of mechanistic interpretability, in the same sort of area that you've just heard from Hoagie. Perhaps to categorize the difference, we were taking more of a bottom-up approach to finding features rather than a top-down, because we were interested in a specific feature of interest a priori, which is sentiment. You know, text sentiment is perhaps one of the most ubiquitous and obvious and natural features that you would want to find or study in text. And we wanted to see, yes, could we find some representation of this feature within a language model. So the way that we began this was we took about the most simple data set that we could imagine, which was a set of prompts of movie reviews, which we hoped would induce the model to tell us what it believed was the sentiment of that movie review, using the language model's natural ability to predict the next token based on the way that we structured those prompts. So this was a data set of prompts where they only had two valence tokens. There was an adjective and a verb, which are natural ways of expressing sentiment. So within the data set, those were the only two token positions that were varying. And we looked at the residual stream. So you heard Hoagie talk about the residual stream. It's basically the working memory of a transformer model. At every token position, it can only read and write from the residual stream, and the residual stream at the final layer via the unembedding basically determines the prediction of the next token at that position. So it's a natural place to go looking for features, and the first thing that we did was we visualized using principal component analysis in 2 dimensions what the space of these residual streams at those tokens looked like. And pleasingly, we found that they were naturally clustered, as you might expect. And when you zoomed in on each of these corresponding clusters, you indeed found that on one cluster it was all of the positive words, whereas on the other cluster was all of the negative words. So it seemed to us, from this very basic initial exploration, that there was some structure within the language model's representations that encoded sentiment. A lot more to be discovered at this point, but it suggests that we could attempt at least to go looking for a representation. And based on this 2-dimensional principal component analysis, and also lots of theoretical reasons within the literature why we think representations of features should be linear, we decided to go looking for a single direction that would hopefully represent sentiment. So how do we go finding an actual direction within this large vector space of the residual stream that will hopefully represent sentiment? Well, based on the clustering that we saw earlier, a natural first thing to do would be k-means. With 2 means, you would determine in an unsupervised way 2 clusters with a centroid for each cluster, and then you could draw a line from one centroid to the other that would hopefully correspond to sentiment. We've already talked about principal component analysis, PCA. We saw that in 2 dimensions to observe this clustering, but you could go straight to 1 dimension to determine a single direction that hopefully captures most of the sentiment information in the model. Another very simple and obvious method is just take a positive tokens representation, a negative tokens one, draw a line between them. Do this for all of the examples in your data set. You get a bunch of lines connecting positive to negative. Take the mean over all of those. Another one is to train a classifier or a probe using logistic regression, which will hopefully find a way to separate or split the 2 clusters of positive and negative sentiments. The final method that we used is one of the more modern approaches, and one that I suspect far fewer people will be familiar with, and it's due to one of my co-authors, Atticus Geiger, from a previous work, which is called distributed alignment search, or DAS. So in the same way that you can think of logistic regression as being an optimization-based method, which is trying to find the best possible classifier, from a correlational perspective, the best possible direction, DAS is basically doing the same thing but for causation. So we've had a lot about Judea-Pearl style causal attribution already in this conference, and this is where this idea comes from. The idea is to find the direction which, by some metric of how much it's changing the outputs, which direction is most causally influencing the actual model's outputs. So with those 5 methods in mind, we can find some directions. And fortunately, to simplify the rest of this talk, what we find is generally, particularly for small models, that you get very high cosine similarity regardless of which of these methods that you use. And exactly which data set that you use and so on. It seems to be relatively robust. It seems like they're hopefully all kind of converging on the same answer. So for the sake of the rest of the talk, you can just assume that we have a sentiment direction computed with one of those methods, but we basically just have one direction that we care about. And the question now is, can we really convince ourselves that we found what we think we found, that we found a single direction, a linear representation of sentiment within a language model? So the first way to test this is this correlational approach, where we're going to run the language model on a set of text from the real world. This was done using open web text from Hugging Face. And at each position, using color, we're going to visualize whether what I'm going to call the sentiment activation, as in, if you take the residual stream and then you project the residual stream onto this direction that we believe is the sentiment direction, you get some number, which is a single floating point number. And so we can visualize that at each position very easily. So blue is corresponding to one side of this axis, and red is corresponding to the other side of the axis. And indeed, what we find, if you look at the words that light up blue, they look like they are very positive, sentiment-y kind of words that we would expect. And similarly, red ends up being very negative. So you can see those in A, B, and C there. That's done using GPT-2 small. We also did this analysis with some slightly larger models that can do a bit of other languages, which was interesting, because we trained these directions exclusively on this toy data set that I explained at the start, using simple English adjectives only. And not only did it seem to extend to verbs and adverbs and nouns and so on, but it even extended into French. When we put the opening paragraph of Harry Potter in French through the model, the sentiment activations that came out seemed to make sense. It was picking up words like perfectly and good as being positive sentiment, and vice versa for negative words. So at this sort of qualitative level, it looks like on a real-world data set, these directions are coming up as meaningful and seem to do what we think they're doing. But to make that more quantitative, what we did was we binned the sentiment activations, and we sampled for a bunch of times from each bin, and we submitted those words and the context of that word from open web text into GPT-4 as our sort of oracle or our ground truth labeler. So GPT-4 had the final say of whether this was genuinely a positive sentiment or negative sentiment word or not. And what we found was, when we took a word from the left-hand side of the x-axis here, so very negative sentiment activations according to our small model like GPT-2, and we submitted those to GPT-4, we found that in the red area here, the vast majority of those were indeed labeled as negative by GPT-4. Basically nothing is positive and a tiny bit labeled as neutral sentiment. And similarly on the other side of the x-axis, we find yes, in the tails of the sentiment activation, GPT-4 is saying yes, these are very negative versus very positive sentiment words. So at a correlational level, it seems like, yes, we found this direction, and when you look at this sentiment activation, this single number that we've taken from the residual stream space, it seems to pick out positive versus negative sentiment. But the question remains, again, we have lots of fans of Judea-Pearl style causal attribution here. Is this actually how the model is completing sentiment-driven tasks? Is this actually how the model knows to predict a positive or negative next word within the movie review? That remains to be shown. So to do that, we used a technique called activation patching. So this is a technique originally from causal attribution analysis and sort of become very popular within mechanistic interpretability. The idea is that you have two different prompts, each with their own forward pass. And what you do is, as you go through the forward pass of one prompt, you patch or substitute in an activation from the other prompt. So what this looks like in our case particularly, where we really are caring about sentiment, is we have a positive sentiment prompt and a negative sentiment prompt. And as we go through the forward pass for, let's say, the positive sentiment prompt, we patch in just the sentiment activation, so just that single direction in the residual stream space from the other prompt. And then we look at the outputs and see, was this sufficient, this single externally driven change, was that sufficient to change the model's outputs, to switch it from a positive prediction for the next token to a negative one? So there were two different quantitative metrics that we used for this. One was the logic difference metric. So the idea is that to get a sense of whether the model is predicting a positive next token, we would take an example positive next token like great and a negative token like terrible. We would look at the output logics for those two, take the difference between them, and that gives you a sense of whether the model is predicting a positive or negative next token. So you can check what that number is for a positive prompt and for a negative prompt. And then when we do this patching experiment, we'll presumably get a logic difference somewhere in between the two. And we can therefore create this normalized, kind of smooth measure of the logic difference from the results of our activation patching experiment. As well as that metric, we also use the logic flip metric, which is basically a discrete version of the same metric. It's simply a 0 or 1. Did we successfully flip from more likely to be positive to more likely to be negative for the completion? So, what did we find? This is our toy data set of movie reviews that I explained at the start. What we found was we basically could completely flip the prediction. 100% here means we've completely gone from negative to positive or vice versa. Whether you looked at logic difference or logic flipping, basically 100% of the prompts we flipped the prediction. So it seems like this single direction residual stream space was indeed sufficient to be causal within those prompts, even out of sample. At least using DAS. So DAS is what we expect to do the best here, because as I explained at the start, DAS is the direction finding method which is specifically optimizing for being causal. So when we look at the results of these causal interventions, we expect it to show up at the top here. We got good results for many other directions, but that was always at the top. So that's a neat result, but does this apply in the real world? That was just a toy data set that we constructed that was useful so that we could compare across a variety of model sizes which might not be able to handle classification of long movie reviews. So for that, we used Stanford Sentiment Treebank, this very useful data set of human annotated movie reviews from Rotten Tomatoes, which has individual clauses labeled as being positive or negative. So we had this big data set of lots of genuine movie reviews, and we could feed that into the model to see whether it predicted positive or negative completions. And so using the directions that we had trained on this tiny toy data set of English adjectives, and then evaluating that using this activation patching experiment, we found that we could flip more than 50% of the predictions from positive to negative using this patching, which is a remarkable example of how a toy data set can give you remarkable insight to predict in the real world. We did a second verification of the causal efficacy of these directions, which I want to share with you. So instead of using activation patching, this experiment was using activation steering. So it's a similar idea, but instead of taking sentiment activations from actual values from a positive and a negative prompt, we instead just said, okay, sentiment activation, that's just a number. let's add a very positive or negative number to it and see what that does to the model's outputs. We then generated a bunch of completions and again fed them to GPT-4 to tell us were those completions positive or negative. And what we found was that when we added a very negative number to the sentiment activation on the left-hand side of the x-axis here, GPT-4 generally labeled those as somewhat negative or negative, and similarly on the positive side of the axis. So the combination of all these experiments convinced us that yes, that this is actually a direction which is not just classifying, containing the information that allows you as a human to come along and split positive versus negative sentiment, but it is actually something that the model is using to determine its predictions. An interesting phenomenon which we also observed in the course of this analysis is something that we call the summarization motif. So what we did was this circuit analysis in GPT-2 small to see how does it accomplish the task exactly, which, GPT-2 small has 12 attention heads in each of 12 layers. What's going on here? How does information get moved around the model between positions in order for it to generate its predictions? What you would probably think naively is, given that, as we said, there were only 2 positions that were different across the prompts and that really contained the information of the sentiment, you would think that basically attention heads would read these positions, write it to the end position, which would determine the final output logits. And indeed, for many of the heads which affect the output logic, this was the case. But there was this second pathway that was not the majority, but was significant enough to be noticeable in GPT-2, which was that there were these other attention heads that read yes from those adjective and verb positions that contained the sentiment information, but then they wrote to the word movie, seemingly this sort of irrelevant token which contained no information. It was constant across all the prompts that we gave it. And then there were these other heads that we called summary readers, which read from that position and wrote to the output logits, which affected the sentiment of the output. So this gave us the intuition that there is like the potential for this sort of placeholder token positions where you can get these bottleneck activations where a load of information gets funneled through a single position that you wouldn't necessarily expect in advance, that the model can write to it and then use that information later, even if it doesn't have any information that's relevant on its own. So in order to test that this actually occurs and is significant, we did some experiments, some more activation patching experiments, this time using Pythia 2.8b. At the time, it was an obvious open source sort of 3 billion parameter model to use. We've since replicated similar findings with Gemma and Quen and other families of models around a similar size. And we gave it another toy data set, this one we call Toy Mood Story, which had descriptions of a character like Jack and whether he loves or hates parties and whether he's in a good mood at the party or not. So again, it's expressing some sort of sentiment. And what we did in this first experiment, 4.1, was the prompt had a clause containing the sentiment information followed by a comma. And in 1.1 here, what we did was we patched the actual clause, the text which actually contained the valenced information, whereas in 1.2, we patched just the commas. Patching the commas in like layer 0 would have 0 effect because the commas are constant between the positive and negative prompts. It's just a comma. But in intermediate layers, if the model chooses to write some information to the comma that it wants to use later, then patching the comma at that layer could affect the output logic significantly. And indeed, when we computed the logic difference metric from before, we found that it didn't matter quite a lot. It was sort of a comparable number whether we patched the commas or the actual phrases themselves, that these were sort of similarly important in contributing to the overall ability of the model to distinguish the sentiment of the character in this story. So we got very, very close to a sort of 1-to-1 ratio here of which was more significant, the clause or the summarization position. So we wanted to know, could we find a way to get it over the top? Are there some conditions under which this ratio would exceed 1? And indeed, we found that when we extended the prompt to be a full sentence rather than just a clause followed by a comma. And we repeated this experiment, patching either the clause or the period at the end of that sentence, and then injecting some amount of irrelevant text into the middle of the sentence. We found that as we increased the amount of irrelevant text, this ratio increased. So if you added enough irrelevant text, eventually the model would decide, okay, I'm actually going to rely more on the summary that I wrote at this period than going back all the way to where the original information was. Which we found really interesting as, this trend of language models getting longer and longer context lengths, and being able to use that context length properly provides a sort of tantalizing glimpse that maybe these effects could become more significant over time. And finally, just to check, these same results do hold up on not just toy datasets, but in the real world. Again, looking at Treebank. This time we did an ablation experiment. So by ablation here, what I mean is that running the model through all of Stanford Sentiment Treebank, you get a bunch of different sentiment activations. We can take the mean over all of these sentiment activations to get some kind of neutral sentiment. And then we can replace all of the sentiment activations with just that one number, so it's constant. So we're just sort of erasing all information that the model is storing along the sentiment direction. And what we found that doing that dropped the classification accuracy by 38%. But we found that if we did that same thing, only ablating commas, seemingly something which shouldn't contain any sentiment information, it dropped the accuracy by 18%. So in accuracy terms, again, sort of almost half of the effect was at these summary positions, just at punctuation. So just to summarize the findings and our contribution in this work, what we see as our value here as a case study of a situation where you have a feature of interest. How do you go about using all of the tools that exist out there in the literature for mechanistic interpretability and causal attribution to find a representation of that feature within a language model? And obviously, it would be great in the future to find features that are relevant to safety with similar methods. And the findings that were novel here were that there actually was like a single direction, a linear representation of sentiment that was causal and was sort of robust to different data sets, different ways of fitting the direction. We seem to be converging on a single direction that represented sentiment. And finally, we had this surprising thing that sentiment information isn't just stored at words that are inherently expressing sentiment, but also at these punctuation kind of positions where there isn't any information otherwise, but the model can choose to summarize or store information for later retrieval. Thanks, and I'll take any questions.
Thank you. Questions for? Let's go with a new voice from the right-hand side of the room.
It's very interesting about the influence of commas on the sentiment analysis. Japanese language doesn't use commas as much as English. It doesn't have punctuation besides like the final dot. Do you have any idea why commas are so important in English in terms of sentiment analysis? And could you guess what will happen for languages that don't have commas like Japanese?
Yeah, that's a good question. So we've done some work on this after writing this paper. And my intuition at the moment is that it's very important for a language model to sort of remember a lot of context when it gets to something like a comma or a period or a new line, because otherwise, that comma itself doesn't tell you anything. Commas have very little inherent information to them. And so in order for the residual stream at that position to contain all the information that the model needs to make a good prediction of the next token, it sort of needs to have remembered a lot of previous context and written it to that position. So it can be like, oh yeah, I'm in the middle of an English sentence talking about movies. And so I expect that in those kind of situations, you'd find a lot of information being summarized, whereas, if you went to a random word within a sentence, there might be more context from the word itself that would enable you to predict, oh, this is going to be a positive sentiment adjective next. So I think that it's sort of a compensatory mechanism for the fact that at these positions like pronouns and commas and periods, that, yeah, it needs to store this extra context. In terms of other languages, I think there's been, since we wrote this paper, there's been some very good work by other authors looking at this. I think it depends a lot on on what the corpus looked like that trained the language model and so on. I think a lot of authors have recently speculated that the model sort of the model often has like particularly GPT-4, say, seems to think in English, and if you ask it in other languages, it kind of has to translate between English and that other language. So yes, I don't know enough about Japanese to make a fully informed guess, but I suspect that what would happen, assuming it was the kind of model that is really thinking in English, is that at positions where there would be a comma in English, then it would store these kind of summaries. But it would be very interesting to see.
Other questions? Let's go with Kai in the middle.
Hi. Do you think that language models that have a sort of proper working memory might have a bit more interpretability in the sense that they could properly summarize things in working memory rather than have to put them in the context because they just have nowhere else to put them? So I guess there might be related work with the sort of vision transformers need registers, where they saw that because vision transformers don't have memory, they put things at weird background pixels in order to compute, and then they gave them working memory, and they put the computation there. So do you think, similarly for language models, this might be a way to get more interpretable representation just because they don't have to shove it into commas and periods and stuff?
Yes, I definitely think that the current paradigm of transformers and the residual stream is somewhat, I want to almost say cursed, but challenging for mechanistic interpretability, in that there's just like so many different kinds of features and information that is getting compressed into this relatively small vector space. And yeah, I think if there was more of a natural place for this information to be stored, it would probably be a lot more interpretable. That is the sort of the dream of SAEs, is to, sparse autoencoders, as to who he was talking about, to try to fix the mess of the residual stream and recover something which looks a bit more like a working memory. Yeah, I don't know if transformers are here to stay. If they are, SAEs are sort of a backup hope in that direction. Otherwise, yeah, perhaps if RNNs or something else becomes more of the dominant paradigm, I think this could change a lot, and it could well end up being easier for mechanistic interpretability if it did.
Okay. Sadly, that is all we have time for. However, we're about to go into a half-hour coffee break. One last chance to have a look at the posters, schmooze with the speakers, ask any remaining questions you might have. So, thank you very much, Oskar.